Our final chapter this semester is Chapter 5, Exponential and Logarithmic Functions. We're pretty much going to do a brief overview of this chapter, and we'll have some application with it on our final. Lesson 5.1 is all about exponential functions and their graphs. You're definitely going to need a calculator for this lesson. Make sure you have one, and down below I'll show you how to navigate and find key buttons on your calculator to help you with this chapter. An exponential function is any function where your variable is the exponent. So in this example, f of x equals a to the x power. A is known as the base of the function. And a can be any number it wants to be. X itself, the variable, is your exponent. And as that number changes, the graph will change pretty significantly. Exponential graphs are known as non-linear graphs. And as you look at the graph on the right, you can see that it's really close to the x-axis on the left side, but as x gets bigger, all of a sudden the graph gets really big on the right-hand side. Over on the right, it says, notice the graph does not go below the x-axis. This is common in exponential functions. It says a line that a graph approaches but does not cross over is called an asymptote. You maybe remember this word from Algebra 2 last year. Now this isn't on your note packet, but this is going to help you navigate a particular calculator. So if we look at these three types of calculators, the first one is a TI-30. In order for you to navigate through exponents and logarithms, you're going to want to look at the functions over here on the left-hand side. So we have the log function right here, the ln function, there's the e button, and then the 10 to the exponent button. Those are going to be the buttons that you'll navigate and use this chapter. In the middle, we have a TI-34. And what you'll have to do is hit the second function and then the log button, so actually the PRB button. And you'll be able to arrow down and over till you find what function we're looking for. On a graphing calculator, your function buttons will also be on the left-hand side in this section right here. You see there's the E button right there for exponents, there's the 10, and we'll also use the logarithm button and the ln button. So making sure you know where those functions are will be helpful throughout this chapter. Remember when graphing, like I said up above, this function will be a non-linear function. And the asymptote for this kind of parent function of an exponential is going to always be at y equals 0, which is also known as the x-axis. So it says compare the graphs for f of x and g of x. You'll notice f of x is 2 to the x power and g of x is 4 to the x power. They both start small on the left-hand side when x is small. But as x increases, notice they both increase extremely quickly. Notice for each of them, we have a base of 2 and a base of 4. The graph that gets bigger faster is the one that has the bigger base. So g of x gets bigger faster than f of x does. Where over on the right-hand side, if the bases are fractions, it gets smaller faster. So the smaller the fraction, the smaller the graph becomes. These are both examples of exponential functions when the base is an integer or the base is a fraction. When working with base e, this is where you're going to want to have your calculator. Base e is actually a value that's similar to pi. It's kind of a constant value that we use quite a bit in exponential functions. The value for e is approximately 2.71828, and that repeats. And e is known as a natural base. It's used pretty often in exponential functions. It says use a calculator to evaluate f of x equals e to the x power. So we have that graph over on the right as kind of a visual, but we're going to want to use the calculator to evaluate to 3 decimal places. So if f of x equals e to the x power, we're just going to plug in different values for x and see what we get. When x is -2, take a look at the graph. At -2, our output's just barely above the x-axis. So what this means is we're going to plug that in for x on both sides of the equation. So on your calculator, you're going to want that E function to show up. You may have to hit the shift or second key to get it. For those of you with the TI, oh goodness, which one was that? The TI-34s, you're going to want to do second log and arrow down till you find E. Raise it to the exponent of -2, and this answer is pretty small. It's about 0.135 if we go 3 decimal places. E to the first power, if we go 1 to the right, you can kind of see how it's up here. So it's between 2 and 3. Therefore, if we plug that in, f of 1, we're going to type in E with an exponent of 1. And that's approximately 2.718, which is how we defined it up above. As x gets bigger, our answer should get bigger faster. Exponential functions grow really fast. So if we were to plug in 5.2, notice we don't have the graph big enough for that over on the right-hand side. Therefore, we do need our calculator to help us with this one. If we plug in E to the 5.2 power, you're going to get 181. That's pretty big. About 272. And if your x value is negative, so going to the negative location on the x-axis, notice on that left-hand side the graph is really small. So what that should indicate for us is our decimal should be small as well. If we raise E to the -5.2 power, type that into your calculator and you're going to get approximately 0.005 or 0.006, depending on what that other number was. And there you go. Those are just kind of ways to utilize that E as a base on your calculator. One thing to note on this, everybody, is using that kind of asymptote right along here, the x-axis, notice nothing goes below it. All of our values are positive, so we get positive outputs each time. One way to utilize exponential functions is determining interest on an investment. This usually is intriguing to students as you want to start saving money for things in the future. Investing money can yield your interest compounded at various times in a year. The formula you use is A equals P times 1 plus R over N to the NT power. It's a pretty aggressive formula. Capital P is the original amount that you're going to invest. So maybe you're putting money into a savings account or something like that. The R value is your percentage rate. So the percentage rate that the bank would offer you, you want to convert it to decimal form. N is represented twice in this equation, and N is the number of times your interest will be compounded in a given year. T is the time that your investment is at the bank, earning interest, and then A is the new amount. So the fixed values in any equation should be P, R, and T. The N value, the number of compounds possible, is interchangeable, and that'll be what helps determine your new amount. So it says, example, Mrs. Fry invested $12,000 at an annual rate of 3%. Find how much money she would have in 5 years if interest is compounded in a variety of different fashions. So taking a look at the given information right away, if I invest $12,000, that's my principal, that P value. So that's going to be constant. That number won't change for any of these problems. The rate, it says, is 3%. That also won't change. But if the rate is 3%, what we need to do is convert that to a decimal. Moving it 2 places to the left, that would be 0.03. And that's the value we'll use. How much money would she have in 5 years? So 5 years is the total amount of time I want my investment to earn interest. T equals 5. Again, P, R, and T should always stay the same. So here's what's going to be interchangeable. All of a sudden the screen got really big. If you're going to compound interest yearly, yearly means just once a year. Therefore, N equals 1. If we plug in what we know to our formula, A is going to be the new amount we have over our extended period of time. P is 12,000. And then it's 1 plus R over N, so 0.03 over 1 to the NT power, 1 times 5. And then we just simplify. So it's very easy to plug in the parts that you know. They should stay pretty consistent. 12,000 on the outside. 1 plus 0.03 over 1 is simply 1.03 to the 5th power. Now you should be able to enter that all in at once on your calculator. 12,000 and then parenthesis 1.03 parenthesis, and use that little caret function to raise that to the 5th power. After 5 years at this percent, I would have approximately $13,911.29. Make sure you can plug that in to get the same amount. When you're ready, let's try quarterly and see what that does to the amount we'll have after 5 years. Quarterly means once every 3 months, or 4 times a year. That changes our end value to 4, but everything else will stay the same. A equals 12,000. And now our parentheses is going to be a little bit more intriguing to figure out. 1 plus r over n, so that's going to be 0.03 over 4, to the 4 times 5, or n times t, power. What you want to do in the parentheses is just make 1 a fraction and get a common denominator. So it really isn't that difficult. 12,000 on the outside. A common denominator of 1 and 4 is just 4. So that would give us 4 over 4 plus 0.03 over 4. And then 4 times 5 will be the 20th power. If we add the numerators together, this gives us 12,000 times 4.03 over 4 to the 20th power. And you should, again, be able to type all of that in at once. Just be careful with that parenthesis, 12,000 and then parenthesis 4.03 divided by 4, parenthesis, to the 20th power. You'll notice we get a little bit more money than our last possible option. We end up with a total of $13,934.21 after 5 years. So as the number of compounds increases, you should get more money over an extended period of time. Monthly, let's see what that's going to mean. There are 12 months in a year, so this means you would earn interest on your account 12 times. Now, a bank likely isn't going to give you that as an option, but if they did, that'd be pretty awesome. All right, let's see how much money we'd have. So we'd have 12,000 again. 1 plus r over n, which is going to be 0.03 over 12. We'll do that common denominator thing again. And then n times t is going to be 12 times 5. Let's put 1 over itself and get that common denominator. A common denominator of 1 and 12 is just 12. So it's a big formula, but it's pretty manageable to work with. And on the outside, the exponent 12 times 5 would give us 60. All right, so we have 12,000. 12.03 over 12 to the 60th power. All right, please type that in. If you haven't been doing so, try it at least once to make sure you can do this independently. I'll put a squiggly equals there. Do you end up with more money than you had for quarterly and yearly? Hopefully you get an answer of yes, but it's not as significantly different as it was from quarterly or from yearly to quarterly. That was a bigger jump. Let's see, I got $13,939.40. So it's better than nothing. It's better than not having a change at all, but it's starting to kind of slow down a little bit. Okay, last but not least, we have daily. Let's see what happens if we have daily compounded interest. There are approximately 365 days in a year, so that's what we'll go with compounding. I know on leap years there are 366, but we'll stay with 365 to keep it consistent. If we enter all of this in, we have 12,000. 1 plus 0.03 over 365. Now that decimal on its own would be pretty small. And then we raise it to the n times t power. That exponent's going to be big. So there's kind of the balance there in how we're going to get our interest over time. Getting that common denominator, we'll have 12,000, 365 over itself. Let's see here. Okay, and then, 365 times 5. If you enter that in, our exponent is going to be 1,825. All right, we're getting there. 12,000. One more round here. Add the two numerators together, 365.03 to the, 1,825 power. Enter all of that into your calculator. And after 5 years, if a bank gave you interest daily on your investment, you would end up with $13,941.92. Obviously, out of the 4 choices, that would be the best deal. Technically, though, you could go smaller yet. You could go, instead of monthly, you could do, or daily, you could do hourly. You could do every minute, every second. That would be kind of crazy. But as n increases, it would approach infinity. If it ever got to that point, the interest would be compounded what's called continuously. That might be a word you remember from Algebra 2 last year, compounding interest continuously. If that happens and you see this key word, the formula changes from that big formula with a parenthesis to a base of E from the other page. The formula becomes A equals P times E to the RT power. So E is your base. We don't plug anything in for E. P, R, and T stay the same. So it says if Mrs. Fry's investment was compounded continuously, how much would she have? This should give us the biggest output out of all of our options. So if it says continuously in the problem, we can go right to this PERT, P-E-R-T formula. Our original amount is $12,000. Our base is E, so we don't change that at all. We're going to actually type E in on our calculator. Here's where we have to be careful with our exponent. R is our rate, so that's 0.03, and T is time, so that's 5. We're actually going to multiply those two together, and that would give us 12,000 times E. 0.03 times 5 would be 0.15. So we'll actually raise it to the 0.15 power. Make sure your exponent is simplified, and then we plug it into our calculator. We'll type 12,000, and then you maybe have to hit that shift key again to get E to show up. Raise it to the 0.15 power, press enter. Is your answer bigger than any of the choices up above? Our goal is to have it be yes, and it should be, but not by much. So we really don't get a whole lot extra for that continuous compounding from what we did for daily. I get approximately $13,942.01. So these are formulas that are exponential in nature, some of them using compounding for different values, and then some of them when it's compounded continuously. Last but not least, we have a tiger shark problem at the bottom. It says the length L in centimeters of a tiger shark can be modeled by the function L equals 337 minus 276 e to the negative 0.178 t power. And it should say where t is the shark's age, not their t is the shark's age. A couple of typos there. Sorry about that. So the shark is going to be, its age is going to be in years, and the formula is describing length of the shark as a function of time. Our first question, what is the length of the shark when it's born? So if we want to know what length is, we need to know what to plug in for time. When a shark is born, they're not 1, they're not half a year, they would be 0. It's like their initial height or length. So when the shark is born, time would equal 0. So if we substitute 0 into our equation, the length is modeled by 337 minus 276 times e. Ooh, watch that decimal up there. Negative 0.178 times 0. Well, 0 times anything stays 0, so that becomes 337 minus 276 e to the 0 power. You should be able to type that all in at once. There are no no parentheses on this one. And if we do that, the tiger shark would be initially 61 and then centimeters long. That's the length of a tiger shark when it's born, on average. Then it says, what is the length of a shark that's 3 years old? Well, now we know time would equal 3. If we substitute that into our equation, we get L equals 337 minus 276e. And again, watch your exponent here, negative 0.178 times 3. So I actually want to make sure we enter this in to get the correct decimal before we plug in everything at once. 337 minus 276e. If we take negative 0.178 times 3, I got negative 0.534. So make sure to condense that exponent down to one value and then type that all in at once. And this, we get an approximation. The tiger shark would be approximately 175.68 centimeters after 3 years. And there is lesson 5.1.